Young Kim's going to come up here and enlighten us on some things to consider when you want to get into agriculture and drones. Please welcome Young Kim. There's your clicker, forward, laser. Sorry.
Bring this down. Yes. Yeah. Good morning. Before I get into my presentation, I want to share an ironic story with you. I got exposed to unmanned systems back in 2002, and then I got sidetracked a little bit and ran a semiconductor company out in the valley. After that, I moved back to Georgia. You all can tell with my southern accent, I'm sure. And I wanted to get back to my aviation roots, to the aerospace. I flew for the Air Force. By the way, as clarification, that's U.S. Air Force, okay? Wanted to get back to the aviation and unmanned systems, and it's ironic for me to come back here in San Francisco to give this talk about unmanned systems. Now you've got this drone valley going on and so forth and so on, so it's a very vibrant community. There's times when I wish I would have stayed. So with that, I'm going to take you on a personal and a professional journey. So hopefully some of the scars that I'm about to convey to you will be of value to the unmanned systems community, and particularly those who are looking at agriculture as an application. So you hear a lot of impressive numbers, and hopefully I can shed a little bit of cold reality to those and put those in context. So I was the CEO of a company from 2007 to 2012. We did flight automation for unmanned systems. We did things like taking helicopters that are man-sized and converting them into a fully autonomous system. And so I had this arrogance of, I'm in unmanned systems, my customers are the DoD, we provide technology solutions to DARPA, Air Force Research Lab, all those things that would make someone like myself fairly arrogant from a technology perspective. And in 2008, we had an Argentinian customer that came to us and asked us to take our technology and convert a manned helicopter into an unmanned helicopter as a robotic crop sprayer. And I said, go away. I'm busy servicing real cool customers, doing cool stuff. He was very, very persistent. It turned out he has a PhD in economics from the London School of Economics. And as all good economists do, he came with lots of data. And that's when I saw the light, when he came to me and showed me how big agriculture is, what the potential for unmanned systems could be. So that was in 2008, so I've been in the agriculture space since then. So in 2011, I started the first UAV conference focused on agriculture. Before, people talked about it in the press and so forth. And today, all I do is ag. All in ag. So with that, this title, Digitizing Agriculture, is an empty phrase to you, but I'm hoping by the end of the presentation you'll have some depth and appreciation for what we mean by digitizing agriculture. So the question, why ag? You see impressive numbers, and here's an impressive number. Each of those tiny pin dot represents $20 million of cash exchange for crop in the United States. And that was back in 2012. The census is taken every 3 years, so we'll get one of these updated numbers later this year. But that's an impressive number, and that was $212 billion just in the US, and that's annual. That's not over decades. That occurs every single year, and that number will go up every single year in aggregate. Big market. However, most of the economic impactful decisions for those $212 billion is based on an analog signal. And what do I mean by that? Sort of a nerdy way of saying a grower will do something at a farm when he sees something. It's analog. When he does that, then he reacts. So he's making a reactive decision based on a lagging indicator. And as technology folks, when we look at industries that has transitioned from that kind of decision making to using technology that allows you to make predictive decisions using leading indicators, we see markets transform. This is very similar to the 757 Boeing aircraft. I flew in here a few days ago, and as we're in transit, that engine is communicating its condition not only to the engine manufacturer of GE, but it's also communicating that to Delta, saying in 50 more cycles, I'm going to predict I need to come in for maintenance. These things occur all the time in vast industries, and I think agriculture is going to go through that similar transformation. That's why we get excited. So let's bring this home a little bit more personal level. That's my 9-year-old son, my 2-year-old daughter in our backyard. We had a lot of snow in Virginia. Of course, my wife is taking the photo. And we live in about a 2,700 foot, moderate neighborhood, middle-class neighborhood. To sustain our lifestyle, it takes 7.4 planets to sustain our lifestyle. And then if you look at the food and all the things and energy and resources that is required from a global acreage standpoint, requires almost 33 global acres to support people like my family. So you hear a lot of impressive numbers of, the world population is going to be at 10 billion in 2050. That's too nebulous for me, but it strikes home to me when you're saying there's 1.5 billion of us living in a middle-class lifestyle, and that number is going to go to 4.5 billion. Those are going to be some extreme constraints on resources. This is where technology like unmanned systems, data analytics starts to make an impact. This is why we get excited about transforming and digitizing agriculture. But that's not a lot of time. 2050 seems like a far away, but as folks in agriculture, we look at this in number of growing seasons. We have 35 growing seasons left. That's a lot of work. So we have to move a little faster. So this is an unmanned systems conference. So let me talk a little bit about what we do with unmanned systems. We let everybody fly, and we even let our agronomist try to launch this hand-launched UAV, and you could tell the propeller is actually folded back. So that's the last time we gave a UAV to an agronomist. And you see his colleagues, an engineer on his right and his technician on the left, kind of smirking at him. We have a 333 on this particular aircraft. We have smaller vehicles, both fixed-wing and rotorcraft. We have much larger platforms. This will fly for about 6 hours. We have communication links where it can go beyond visual line of sight. Obviously, this is not for agriculture in the United States. It's outside the U.S. And then we also have this platform. This is the Yamaha R-Max. I believe we're the only commercial company that has this platform. My team is trained by Yamaha. Yamaha is doing a lot of work at UC Davis over vineyards, and we're doing some work on the East Coast in North Carolina. So this just goes to convey that we've got quite a bit of depth in unmanned systems in agriculture. Certainly multi-rotors and so forth and so on, but much larger sizes. Again, all focused on trying to find that product market fit with unmanned systems within agriculture. So here's some scars. Unmanned systems is not scalable in agriculture, particularly those that are electrically powered like multi-rotors. We have over 400 million acres that are used to grow crops. To make an impact in agriculture over those 400 acres, think about how many of these small electric UAVs are needed to image 400 plus million acres in the United States. That's not scalable, folks. Particularly, it gets worse in the United States when you've got a 200-foot ceiling limit with the 333s. Or, with specific permission, you can raise up to 500 feet. It still doesn't scale. Not only the size, but the logistics of deploying people to a specific field to image a few hundred acres or some of the capable systems, a couple thousand maybe. But to be able to move those teams around during the day and start imaging all that area with an unmanned systems in our experience, is unscalable. In addition to that, the growers do not have any GIS experience. Even if you delivered information to them, they don't have the technical wherewithal to absorb and do something useful. You hear the buzzword actionable intelligence. You know, I come from the military side. We know what that means. It takes a lot of effort to do so. But the people who take those actions are well trained. Growers are not. So unmanned systems on its own, in our opinion, based on our scars, is a fairly weak value. Why? You're taking imagery at a specific point in time. It's one data layer. Photo on your lower left. That has no context. All it shows is variability. You hear these indices called NDVIs and so forth, but all it's saying is, I've got more green vegetation and less green vegetation. And that has some value, but what we have found is that value does not translate into a change in behavior. This becomes a supplemental. It's a nice to have. Oh, it validates what I kind of already knew. But it doesn't change my behavior so that I walk the field less or my crop consultant walks the field less. And I get a lot of pushback when I convey that to the unmanned community. Oh, you get all this information, therefore you can prioritize to go over here and you don't have to go over there. Very true. But unmanned systems is an aerial platform. When you look down on a crop, what you don't pick up is what's underneath the leaves, for example. There's a lot of disease pressure there. So growers and crop consultants will walk that field with more than a singular purpose. They have multiple things they're looking for. And so they will spend a similar amount of time walking that field and perhaps use this to validate what they're doing, but they're not going to not walk that field. And then we made the mistake early on of pursuing these large acre growers like corn and soybean growers. I know you don't know this, and I can't believe I know this, but corn closed at $3.65 this morning, a bushel. And a grower, corn grower specifically, if that price on the market goes below $4, they're losing money. And to then go to those growers who are losing money with a supplemental value proposition and ask them to pay out of their pocket while they're losing money, that's not going to happen. The value proposition must get stronger for it to have traction. The other thing, I can go on forever, a lot of scars. The other thing is with unmanned systems imagery alone, it's tough to see trends. It's a static data layer. What you want to see is patterns as well as point solutions. So you want to see both. So one of the things we realized, we're trying to deliver a microscope, and what the grower really needs is a low-power binoculars. And those don't fit. And it took us a long time, a lot of money, a lot of stress to come to that conclusion. So what do? We went to the unsexy world of satellites. Those are all the satellites that mostly the U.S. government has put up. And we now pull data from a few of these satellites to give you that low-power binocular value, what we call crop monitoring. Crop monitoring is not the same thing as detection. That's what unmanned systems really is good for, but is not good for crop monitoring. But once you add the crop monitoring component using satellites and the detection component of unmanned systems, now the value proposition starts to get more interesting. I did want to mention those in the yellow circles as more and more of these, particularly in this area with Planet Labs, coming online, having ubiquitous 24/7 real-time video. The resolution is going to get better and better. They're going to get more and more sensors on board. So we're anticipating they're going to put sensors on board that allows us to pull that data, add more resolution to our satellite products. We're waiting for that. SMAP, called Soil Moisture Active Passive, was launched in January of this year. It's going to be up for about 3 years. And again, that's another data source we want to pull in to give you another facet of your crop condition. So you can do some interesting things that, again, you couldn't do before with unmanned systems. When I asked a grower, and I was with a grower last week in Georgia, he's growing about 20,000 acres, and I asked him, how do you make your decisions? And he basically said, by the seat of my pants. He has instinct. He's been on that land for many, many years, and he makes it up as he goes along, but he's pretty good. What you don't get, though, again, making these decisions in this analog format, you don't get this really tight coupling of this cause and effect, right? Input, output. Engineers, we like this. We want this to be predictable and repeatable. But if you can't digitize it, you can't run really tight coupling. But now, with a tool like this, you can start to get there. So, for example, I know that's a lot of gobbledygook up there, and so with satellites, we can have historical data. Certainly at the limitation of low resolution of about 100 foot per pixel, but it's really good to get trend data. And so one of the things we can do is you can see that where it says fertilizer needed. By the way, the vertical axis is the NDVI value, or the amount of vegetation. It's a ratio. And the x-axis is time. And so what you can see is where it says fertilizer needed, that sort of pink curve, once you applied fertilizer, you see an immediate response of your crop with more vegetation. That's 1 year. That could be one crop like corn. Let's pick another one. In this case, potatoes, soy. Roundup wasn't ready, right? Therefore, you had a very flattening or a decreasing in your vegetative value. So now you go, here's what I did. Here's how the crop reacted. You start to get this cause and effect relationship. And once you know this with history, what you can do is start benchmarking. So the dotted line on the right is what has done historically for that particular crop over that particular field. And that solid green line on the right is what it's doing today as we're monitoring using satellite technology. And so with that, what do we get? Sorry about that. That's on the left. That should say food and water, physical size, and active growth. So these are, envision, if you will, a grower was blind. Particularly with a customer, for example, where they have 600 fields over 13 states. So how do they know what's going on? What is the condition of the 600 fields over 13 states? They're blind. They get a report sent in by a manager periodically. Now, we can give them 4 different views, if you will. The binoculars I talked about with 4 different views. Food, we look at the chlorophyll index. How well is it digesting food, or is it lacking nutrients? For example, the dark green vertical diagonal strip under food tells you that area is doing particularly well. Then you can start correlating that to water. And by the way, if you can do water in agriculture, you're about 70% there. That determines about 70% of your success. So to be able to tell how well is your crop transpiring or putting out moisture, if you can, when you measure that, it tells you when you need to water and where. At very, very low cost. And then you look at the physical size. We can now look at a corn, for example, grows to a certain stage, and then it starts to shrink because it wants to convert all that photosynthate into the actual corn, not grow more vegetation. That's not good. And the grower now is able to track this changes in physical size without having to send anybody to that particular field using this technology. And then you can then compare it to the vegetative index. So these 4 dials and the interrelation now starts to give you a look into an area without having any resources there. Now, if you want to zoom in on a particular area, that's when you send a higher resolution capability like unmanned systems. So, what we're doing is, although the unmanned systems is at the center, we're interconnecting the data layer from manned aircraft to image lots and lots of acres. still have very decent resolution. And then we're using satellites, interconnecting that data layer. We also recognize there's quite a bit of information that you can collect from ground sensors. So we call this proximal sensing from the ground, or in-field sensing, and then remote sensing from satellite, manned, and unmanned. Once you put those things together, you now are able to do things, not the sort of the better, faster, cheaper, more of the efficiency problem, but more of new capability, because you now are looking at this from a systems perspective or a holistic perspective. So I leave you with this last slide of what we do as a new capability, where now the grower goes, this is something we've never been able to do before. So we did a trial with this customer last year. We got a little under $10,000, and this year they gave us a 6-figure contract. And what this enables them to do is, before you harvest, you're able to predict with fairly high level of accuracy how much crop you're going to get. This early yield estimation. Why is that important? It's really important because all the logistics issues, for example, that you have to contend with. So imagine you don't know how much stuff you're going to get out of your land until you actually harvest it. So your labor, your equipment, transportation, storage, all those logistical trails are all dependent on how much material you get out of your crop. If you had that information before you harvested, the efficiency you gain by being able to cost effectively arrange all those resources is a significant value to our enterprise level customers. There are lots and lots of more examples of that's possible when you start interconnecting these data layers. So my message to our colleagues in the industry in the unmanned systems space, particularly focused on agriculture, do not look at the unmanned systems as a singular tool. It's like playing golf with your 9-iron. You've got to have other clubs in there to do that well. And to us, what we're doing is we're interconnecting these data layers, really deliver new capabilities. And then once we do that, later, as growers and the community starts to adopt this technology, then you can deliver things like efficiency values. With that, I thank you.